Hello, my name's Grace, and today I will be going over how to do logical equivalence proofs in 203. So right now what we see in front of us is a problem where we're trying to prove a proposition is a tautology. This proposition here is a tautology, so it's always true by using logical equivalencies. And so in this class, logical equivalencies are just propositions that have the same truth values. And so generally, the logical equivalencies that we're going to be using fall into these two tables, specifically all the ones in table 6. So you'll see a lot of the times we will use like identity law or like distributive law or De Morgan's law. Those are often used in this class, as well as table 7. There's also table 8, I believe, but generally these two tables are enough, and they're enough for this problem here, so that's why I only have these two tables at the moment. But generally this first logical equivalency, P implies Q, is equivalent to not P or Q. That is used very, very often in this class, and how we cite that is we often call that the definition of implication. You can write out the whole implication, or you can just write out the implication sign, or we can just directly cite table 7.1. That refers to table 7 and the first row. So if you want to use any of these other logical equivalencies, you can, and you would just cite, for example, table 7.2 for the second one, and 7.3 for the third one, and so on and so forth. So for these logical equivalencies, you notice that they're mostly expressed in terms of PQ and sometimes with R. That P and Q can refer to any proposition. So for example, maybe we're looking at, let's say we're looking at the commutative law here. So this one has P or Q is equivalent to Q or P. These P's and Q's can refer to any proposition. So for example, we could have something like R and S or T or something like that. We can use commutative law on this. You can just think of this R and S as this P here and this T as this Q here. And so when we want to use the commutative law, we would have this is equivalent to T or R and S. So don't lock yourself into the expression of P or Q itself. It can refer to any sort of proposition. Now that we've cleared those, let's dive into the problem. So we're trying to show that P and, let me write that down, P and P implies Q is a tautology. So that's essentially, so in the end, we want to arrive at this is equivalent to true. So that's going to be the last step of our proof. So let's dive in and go through this proof. So with logical equivalence proofs, there's a lot of ways to prove them. Oftentimes we start with people can do steps in many different orders, so there's many different outcomes. But generally, the first step is when you see implications, we want to change those into like ands and ors. Why is that? Is because if we look at table 6 here, none of these logical equivalencies have any implications in them. So it's really hard to use, or it's impossible to use any of these rules in table 6 without getting rid of the implication. So generally speaking, step 1 is to remove the implications, and that's what we're going to do here. So we have this expression here is going to be equivalent to P and then this is P implies Q, so we're going to use this the first row of table 7 to break that implication down. So this becomes P and not P or Q implies Q. And for logical equivalency proofs in this class, you always have to write the rule you use. So in this case, I will just write table 7.1. Again, for these ones, you can write table 7.1, definition of implication. Either of those work. Next, we see that we still have one more implication sign to get rid of. So again, I'm just going to go in and use the definition of implication and break that down. So we would think of this whole big chunk here as this P, and then this part here as the Q. So we'd get not P and not P or Q or Q. This is also from table 7.1. Notice that we haven't dropped any parentheses. It's very important to keep all your parentheses throughout. So we see that this parenthesis here is still here, this one here is still here. Oftentimes people drop parentheses and you get a whole different thing. So like, for example, maybe you would have like not R and S. That is completely different from having not R and S. So you want to make sure to never drop parentheses unless like you know, oh, I can combine these together and then I can drop the parentheses. Generally, make sure to keep them there. It can change your whole proof drastically if you drop them. So after this now, we look and we kind of see what we have here. And so we probably want to deal with this inner part here first because it's the most inner piece and it looks like we could cancel some stuff out when we have that like P and not P together. So what we're going to do is we look at this here and we see that we can probably do a distribution on it, right? This is P and not P or Q, kind of has the same form. I mean, it's of the distributive law with the P, and you can think of this Q here as a not P here and the R here as that Q here. So we're going to apply distributive law here. So we get not P and not P or P and Q or Q, and this is by the distributive law. Next, now we see that we have this piece here, P and not P. This is something that's really nice because this can be simplified down. If you see by the negation law down here, you see that P and not P is actually equivalent to false. So we can just say by negation law, we're going to get a false here. So we're going to get not false. Notice I haven't dropped these parentheses, or P and Q or Q. And this is by the negation law. Oops, oh, why am I not writing negation law? So now we have that. So after now, we see that we have false or something. Now we can again match laws over here. So if we see that when we have P or false, that gives you back P. So right now we have false or P and Q. So that matches. We can think of this P and Q part as that P here. So we can think of getting rid of this false here. So this becomes not P and Q or Q, and that's by the identity law. So now after this, we see that we have this not on the outside. Now, the next step we would think to do is factor that not through because that's basically the only part rearrangement we can do here. So if we want to do that, we will use De Morgan's law, and we notice that with De Morgan's law, the not changes, the and here will change into an or. So I'm going to leave the parentheses here and just factor in the not. So we have not P or not Q or Q, and that's by De Morgan's law. Now, after this, we notice that these are all ors. So next step from here would be to do, we would want to put the Q's together because not Q or Q, we can use that later on. So we would have not P or not Q or Q. So this part here is then by the associative law. Now we have not Q or Q. If we look over here at the negation law again, when we have P or not P, which is the same as not Q or Q, we would have this matches the negation law completely, so we'd get true here. So we'd have not P or true, and that is by negation law. So finally, we have not P or Q. I'm sorry, not P or true. So if we look over here, this matches up with this law right here. Not P or true is equivalent to true. And so we can think of this not P kind of as that P there. And so this is what happens is the true dominates the entire thing. So we would get true back. So in the end, we arrive at this true by the domination law. And so we see that through these logical equivalencies, we were able to deduce from this first expression the final true, like the final value of true at the very end. Notice that we went one step at a time. So for logical equivalencies proofs, it's very important to never skip any steps, generally on exams or on your homework. If you skip some steps, you will get points off for it. So for example, maybe you skipped this distributive and you went directly to the negation law. Like that might result in a few points off on your exam. So you don't want to do that. You want to follow through one step at a time. The exceptions to this is that, for example, if you have associative and commutative, you can do those together. So for example, if I have P or Q or R, something like that, if I wanted to group P and R together, I could do P or R or Q like that. And that would be using associative and commutative together. And that would be okay. That's okay in this class. The other thing that's okay is combining the double negation here into other steps. I don't have an example offhand, but that is an okay thing to combine in with other steps as well. But besides those, you will want to do everything one step at a time. Those are the only exceptions for this class. So with that, this is just how to go through a logical equivalency proof. Thank you so much for listening in, and good luck.